Hi class, let's take a look at problem 14. Now, on problem 14, we happen to have a function that has an exponent that contains another function. So in this case, the best approach is to define that as a function. So technically, let y equals to the x squared plus the values of 2, and then technically raised to the power of x. Now, the next step is to try to get rid of the sign, and not get rid of it, but try to express it in a form where we can actually take a derivative, since the main objective is to evaluate the derivative. So the best option here is to take that log of both sides, because by properties of logs, if you happen to have the log of x to the p, this is equal to p log of x. So if we are able to evaluate a log, we'll be able to drop that exponent and then technically evaluate the derivative of the expression. So at this point, what I'm going to do is I'll just take the ln of both sides. So we're looking at the ln of y. This is equal to the actual ln of the expression on the right hand side, which we happen to have an x squared plus a 2 raised to the sine of x. Now, what this allows us to do is, since you now have the ln of both sides, you can actually drop the actual exponent. So this allows us to drop the exponent and then express the original expression as the ln of y. This is equal to the sine of x times the ln of x squared plus the values of 2. And then at this point, since they want the derivative, we can now take the derivative of both sides of the actual equation. We're going to have a product rule on the right hand side. So I'm just going to label this as F1 G1. And then careful, because on the actual left, we're going to end up with a chain rule. So derivative of ln, it's going to be 1 over the values of y times the derivative of the actual inner function. So in this case, chain rule, and we need to take a derivative. On the right hand side, we're going to be applying a product rule. So this is equal to a sine of x, and then we'll take the derivative of the ln of x squared plus 2. And we need to differentiate this, also a chain rule. And then plus, we're looking at, well, technically the sine of x, which we need to take a derivative of. And then our g function happens to be the ln of x squared plus the values of 2. Okay, the next step, we still have to take the derivative of the ln. Don't forget the actual chain rules on these. And then on the actual left hand side, since we already have the values of y, we're just going to have 1 over y times the values of y prime. This is equal to the sine of x, and let me fix this because that's an x, times the 1 over your x squared plus 2 times the derivative of the inner function. So we still have to take the derivative of x squared plus 2. And then technically plus a cosine of x times the ln of x squared plus 2. Okay, almost done. We just have to take one additional derivative and try to isolate for y's. So y prime over y, this is equal to the sine of x times technically 2x over the x squared plus 2. I'm just putting it on the top, plus the cosine of x. Now, the last portion, it's going to be to restrain the domain. And notice that we actually did a substitution, or I mean, we did we set equal the expression to y. So on our final answer, I'm just going to multiply times y. And then express the derivative of the expression as y prime is equal to, and this is just going to be the sine of x times the values of 2x over x squared plus 2. Oh, I'm missing let me fix it. I'm missing the ln of x squared plus 2. And then we're looking at plus the cosine of x times the ln of x squared plus 2. This entire expression contains the y, and y is x squared plus 2. So x squared plus 2 raised to the sine of x. In this case, well, the only disclaimer that we need is that in the denominator, x squared plus the values of 2, it's not going to equal to 0. And then also, just to mention that some of the actual software problems may want you to put the absolute value there. So you may have a problem where they want absolute value of x squared plus the values of 2. And let me just display the entire problem. That's actually it for problem 14.